The late 1800s was a time when many physicists thought that all the important scientific discoveries had already been made. The classical mechanics that had been founded by Sir Isaac Newton appeared to describe the known universe very well. James Clerk Maxwell had developed the classical theory of electromagnetic radiation, which allowed energy to be transported as oscillating electromagnetic waves. Visible light represents a tiny fraction of the electromagnetic spectrum. Longer wavelength radiation comprises the infrared, microwave, and radio frequency spectrum, and to shorter wavelengths lies the ultraviolet, X-ray, and gamma ray regions. Many physicists thought that there was not much more to be learned, but a few nagging questions remained that classical physics was not able to adequately explain. One of these concerned blackbody radiation. All objects emit light, and as the temperature increases, the light becomes more intense and shifts to shorter frequencies. However, the classical theory developed by Rayleigh and Jeans predicted that the intensity should increase at short wavelengths without limit, in stark contrast to the observed behavior. Max Planck discovered that the predicted distribution could be brought into agreement with experiments if he limited the emitted energy to integer multiples of the frequency times a constant, h. But he didn't know why this should be the case. A landmark experiment was the photoelectric effect, in which ultraviolet light absorbed by a metal surface ejects electrons with very well-defined kinetic energies. By varying the wavelength of the light, scientists showed that the kinetic energy of the ejected electrons was equal to h nu minus the binding energy of the electrons. On this basis, Einstein proposed that light exists not as continuous waves, but as discrete photons, each of which has energy h nu. The value of h was the same as Planck's constant h, and it still bears that name. Just as physicists were learning that light waves have a particulate nature, in that they come in discrete packets or bundles, and we call them photons, scientists also observed that electrons can undergo diffraction from crystal surfaces, as shown here. Diffraction was previously thought to be a property associated exclusively with waves. The French physicist Louis de Broglie put all of this together in a simple equation that says that the characteristic wavelength, lambda, of a particle or wave is inversely proportional to its momentum, p, where the constant of proportionality is h, Planck's constant. One of the important consequences of wave-particle duality is the Heisenberg uncertainty principle, which states that the product of uncertainties in position and momentum for any particle or wave must always be greater than a specific minimum value, h over 4 pi. For example, we've seen that a photon is a partially localized wave packet that can be made up of a combination of waves of different frequencies, or momenta. The more localized the packet, the larger the range of frequencies that is required to form it. Using the de Broglie relation, this approach is equally valid for particles and waves. Meanwhile, still other scientists noticed that the emission spectra of atoms occurs at discrete, well-defined wavelengths and is not continuous, as predicted by classical mechanics. For hydrogen atoms, the lines are few, but for heavier atoms like iron, the lines are many. Niels Bohr created a mathematical model of the hydrogen atom and suggested that the electron could not have any arbitrary kinetic energy as it orbited the proton, but instead was limited to energies associated with integer multiples of angular momentum, h over 2 pi, where h is again Planck's constant. This meant that the binding energy of the electron was equal to a constant, minus r sub e, divided by n squared, where n is an integer, 1, 2, 3, and so forth. The energy of absorbed or emitted light must be the energy difference, delta E, between the initial and final levels. Using this model, Bohr successfully explained the line spectrum of hydrogen, and this served as a qualitative basis for understanding the spectra of heavier atoms like iron. It turns out that although Bohr got the energies right, his classical picture of electrons in circular orbits around the nucleus was wrong. As we shall see, electrons occupy diffuse orbitals that fill the three-dimensional space around the nucleus. But the idea that the energy of the electron is determined by a single integer, n, which we now call a principal quantum number, was correct.